Products of electrolysis depend on the nature of the electrolyte being electrolyzed and the type of electrodes used. Inert electrodes do not participate in the chemical reaction. Inert electrodes act as a source or a sink for the electrons, providing a surface for the electron transfer. Platinum, gold, or graphite electrodes are commonly used as inert electrodes. On the other hand, active electrodes do participate in the chemical reaction. Active electrodes are used in the electrolytic refining of metals, which we discussed earlier. Thus, we can conclude that the products of electrolysis may be different for reactive and inert electrodes. The products of electrolysis reactions depend on the oxidizing and reducing species present in the electrolytic cell and their standard electrode potentials. Some electrochemical processes are kinetically very slow. At lower voltages, these processes don't seem to occur at all. In order to make these processes occur, extra potential, called overpotential, must be applied. For example, the electrolytic decomposition of molten sodium chloride will produce sodium metal and chlorine gas. In this case, only one cation, that is the sodium ion, and one anion, that is the chloride ion, are produced. Sodium ions are reduced to sodium metal at the cathode, while chloride ions are oxidized to chlorine gas at the anode. The electrolytic decomposition of aqueous sodium chloride solution, on the other hand, produces sodium hydroxide, chlorine gas, and hydrogen gas. In this case, besides sodium and chloride ions, hydrogen ions and hydroxide ions along with water molecules are present. Let's look at this process in detail. At the cathode, either sodium ions or hydrogen ions may be reduced. As the hydrogen ion has a higher standard electrode potential than sodium, it gets reduced. However, hydrogen ions are produced by the dissociation of water. Hence, the net reaction at the cathode may be written as the sum of these two reactions. Thus, we have the reduction of water as per the equation shown here. At the anode, too, there are two substances that can be oxidized: chloride ions and water molecules. At first glance, it would seem easier for water to get oxidized than chloride ions, since the electrode potential of water is lower than that of chloride ions. However, the oxidation of water is a kinetically slow process. Hence, an extra potential called overpotential is needed for the production of oxygen. This explains why chlorine, but not oxygen, is produced during the electrolysis of aqueous sodium chloride. The net reactions of electrolysis of an aqueous solution of sodium chloride are as shown here. it is more challenging to predict the products of electrolysis reactions in aqueous solutions. Due to overvoltages, you can't rely solely on standard reduction potentials. Reduction will occur at the cathode, but there are two possibilities for the reduction half reaction. First, ask yourself if the cation is a transition metal or a representative metal cation. Transition metal cations will undergo reduction since they have favorable reduction potentials. Representative metal cations will be too difficult to reduce. Instead, water will be reduced at the cathode, forming hydrogen gas. Predicting the oxidation half reactions is more complicated. It depends on the relative ease with which the different species present in the solution are oxidized. Halide ions will undergo oxidation to form the diatomic elements in preference to water. However, chloride ions undergo oxidation in preference to water due to overvoltage of oxygen. On the other hand, oxoanions are too difficult to oxidize. So, water is oxidized to form oxygen gas. The ability of a cation to be reduced or an anion to be oxidized not only depends on their standard reduction potentials, but also on their concentrations. Hence, to account for the effects of concentration, the standard electrode potentials are replaced by the electrode potentials given by the Nernst equation. In dilute solutions of sulfuric acid, water will be oxidized to release oxygen gas. However, in concentrated solutions of sulfuric acid, the formation of the peroxydisulfate ion is favored. Let's test our knowledge by solving some practice problems.